Today's topic is nonlinear problems in the frequency domain. After a short introduction, we'll look into the harmonic balance method and see how this is related to the finite element method. So we'll do harmonic balance FEM. And then we will see an application example on computational electromagnetics solving the eddy current problem, a nonlinear eddy current problem directly in the frequency domain. So let's look at the solution of a partial differential equation in the frequency domain. We'll consider a time-dependent PDE with a periodic excitation. So this is our assumptions here. And here it is often useful to directly compute the periodic steady state solution. So that means we want to neglect all the transient effects since we're not interested in them, and directly compute the steady state solution, which is of interest. So for linear problems, we already know the superposition principle holds. We can express any periodic excitation by a Fourier series, and we can do a Fourier transform of the complete PDE to obtain a periodic solution for it. And we also know that the steady state solution is unique, so it doesn't depend on the initial condition. If we have sufficient damping in the system at infinite time, we will have only the steady state solution, which is unique. However, if we now go to nonlinear problem, the solution is not as straightforward as anymore. First off, a periodic excitation might cause a periodic solution. This is usually true, but existence and uniqueness of this solution is not straightforward. So for nonlinear systems, you know, you can have multiple solutions possible, and the solution that you get actually depends on the initial condition, for example. Okay, so let's see how we can obtain such a frequency domain solution for a nonlinear problem, if it exists and if it's unique, of course. So for this, we can use the harmonic balance method. And this is most frequently applied to nonlinear electric circuits from where it originates, I think, but also for mechanical systems. So for systems of ordinary differential equations, the harmonic balance method was originally developed. And if you do harmonic balance finite element method, you apply the same methodology to partial differential equations, of course, nonlinear ones. And this is most frequently used in magnetics, for example, for the eddy current problem, for which we will highlight the formulation in the following. And we will follow the PhD thesis by Klaus Roppert. So if you're interested in details, go ahead and look into the thesis. So let's start with the nonlinear eddy current problem. So we're interested in the steady state solution for the eddy current problem. Here A is our magnetic vector potential, gamma is the resistivity, the electric resistance, and mu is the nonlinear magnetic reluctivity. On the right-hand side, we have the impressed current density. So this is given, and it is assumed to be periodic. So we have a period duration tau and a periodic signal. And we also have a nonlinearity in the system, and this is a material nonlinearity coming from the magnetic material property. So typically this is expressed by a nonlinear BH curve. And we're searching for a periodic steady state solution. So also the solution must be periodic, and it must satisfy our eddy current problem equation 45. We don't need an initial condition because the existence and uniqueness can be proved for the case of a monotonically increasing pH curve. And that's usually what we have physically. So in this case, we're lucky. We have a unique solution, and we will compute it via the harmonic balance method. So let's look how we can derive the harmonic balance finite element formulation. As usual, we start from the eddy current problem, and we'll now express the periodic excitation as a Fourier series. We've seen this can be done for any periodic signal. We simply write Fourier coefficients. They are denoted by a hat here, jk. So k is the number of the harmonic. And they can be complex valued in general. We can also write the complex form of the Fourier series, where the jk and j minus k must be conjugate complex in order to yield a real valued signal in the end, which is the physics, of course. And then we do the same Fourier series expansion for the magnetic vector potential. Note that we have chosen to truncate the Fourier series after n harmonics. So of course, this is an approximation. So the equal sign here actually should be an approximation. And then we do the same thing for the solution-dependent magnetic relativity, since also the periodic history of this material parameter, since it depends on the solution, will have a periodic form. Note here that we choose a different order of approximation here. So you could say the order of an m for the material approximation is smaller or usually equal to the order of the approximation of the unknown. Okay, and now we can actually plug this Fourier series expansion into the PDE. This gives us a very lengthy equation with a lot of Fourier series. And additionally, or most notably, we have here a term where we actually multiply two Fourier series, the one for the material parameter nu and for the curl of the vector potential A. And then we can use a trick. We multiply this equation by a to the power of j omega nt for all n from minus n to n and integrate over one period length. So this basically means we introduce test functions in time, so to say, and generate a set of n equations from this single equation. Then you can do some rewriting. I'm not doing this in detail here. So especially this product of two sums you can write as a double sum. To simplify it here, I've already introduced this integral over time. And now you need a few properties of the ansatz functions, which are given here. So look at this property. If you do this integral over the exponential over a complete period, you see that often this integral will be actually zero and non-zero only for certain cases. And if you explore this property, you actually come up with a system that looks that has the following shape. So you have the curl of a matrix expression. So this is actually the product of the two Fourier series that we had. And you can write this resulting sum as a matrix form. And on the right-hand side, you come up with the lines for the different harmonics. And similarly here for the mass term we had, so this was the time derivative of the magnetic vector potential. So the interesting term is the first one, where we had the product of two Fourier series And you can see that you can write this in the following form of a matrix vector multiplication. And the components of this vector here are the Fourier coefficients of the unknown. So this is still the strong form of the problem, but written as a single line for all the harmonics. And now we can apply the finite element discretization in space. And then we can, from each of these lines, get a line that is written in terms of the finite element degrees of freedom. So here these are the A hat underline, again with the indices for the harmonics. And in the system matrices, we now have stiffness matrix and mass matrix. And note that each of these lines here now has the dimensions of the standard finite element system. So if you look for harmonic 1 and you have 100 degrees of freedom in your finite element mesh, then you have for the first harmonic 100 degrees of freedom here in the unknown vector. As similarly, of course, in the right-hand side and in the corresponding system matrices. So each subblock of the system matrix has the size of the usual finite element system. So you see, this will actually be a very large system if you use a lot of harmonics. But in principle, this is what we need to solve. And now we have to look at how we actually can solve this system, since it's still non-linear. We know that the permeabilities, so here we have the stiffness matrices, and they depend on the permeability, which is solution dependent. And here, in fact, these are the permeability for the Fourier coefficients of the material parameter. So let's look at the solution strategy. How can we solve this non-linear system? So first off, we have a large linear system, and typically we use, due to the size of the system, already an iterative solver for the linear system. So here, GMRes or conjugate gradient with appropriate Bloch-Jacobi preconditioner works well in electromagnetics. And in fact, the preconditioner is used from the Paradiso linear solver in our case. We can improve the efficiency quite a bit if we consider that the even harmonics in this case have to be 0. So we can decrease the size to n+1 instead of 2n+1. So that's quite an advantage. However, now we have only solved the linear system. We also have to do an outer iteration to solve the nonlinear system, and this can be done by a damped fixed point scheme, which usually converges rather fast. And in each of these iterations, we have to actually reassemble the system matrices as it contains this nonlinear material parameter and its harmonics respectively. And now we will actually look at how we can compute these harmonic coefficients of the material parameter. And for this, we need to evaluate the nonlinearity in the system. So the pH curve that actually defines our nonlinearity can only be evaluated in the time domain. This is what the physics tell us. We have a B field we get via the pH curve an H value, and from this we can compute the coefficient nu. So in order to do this, we use alternating time frequency switching. So how does this work? So basically what we do when we start the iteration, we assemble our linear system for an initial permittivity nu 0. And with this, we can obtain the frequency domain solution by just assembling the linear system, solving it. We get a solution vector. And this is in terms of the harmonic coefficients. So these are the AKs. And now we can actually use the inverse Fourier transform or the ansatz to transform this into the time domain. So we have in the time domain a periodic solution, and with this periodic solution for each material point, we can evaluate the nonlinear pH curve. And then we get our time signals of the permittivity signal, which we can straightforwardly Fourier transform to get the Fourier coefficients we need in the assembly of the updated system matrix. Then we update our system matrix, assemble the system again, solve the linear system, and get an update for the periodic solution. So these are the main steps. Transform the frequency domain solution into the time domain. There, evaluate the material law, Fourier transform the time history of the material law, and reassemble the multi-harmonic system with these new material harmonic coefficients and solve the new system to get an update. And then you iterate until you obtain a certain convergence criterion. So how is this implemented? Where can you use it? The presented formulations, of course, implemented in OpenCFS, where we have capabilities for harmonic balance FEM for the eddy current problem. So we are using edge elements only in the Mach edge PDE. Just a few considerations when you actually model using harmonic balance finite element method. So of course, the number of harmonics determines the accuracy and the numerical effort. So more harmonics means you get the more accurate approximation, but of course the numerical effort is larger since the linear system is larger. Often a small number of harmonics, so 3 to 5 is sufficient. However, certain systems may require a large number of harmonics. We'll see this later in an example. Also in this example, we'll see the choice of the material law, so the pH curve is important when computing periodic solutions. The mesh resolution guidelines are actually equivalent to the standard finite element method. So there's no difference there. The important thing here, we're dealing with the eddy current problem, so the skin depth must be resolved. Important side remark for the frequency of the highest harmonic. So the skin depth is frequency dependent, and what is important is not the base period, but actually the highest periodic, the highest harmonic we're considering in our analysis. As usual for nonlinear problems, there might be convergence trouble. So just to note the few most often causes for convergence trouble is either an insufficient number of harmonics, unsuitable initial permittivity, so the system doesn't go into a good, so to say, area for the first iteration, or also under-resolved eddy current. So even a two-course mesh can lead to convergence problems in this case. So let's look at an example for an application. This is actually a test suite example of OpenCFS, so you can look into it if you're interested. This is a very easy to understand, well, verification example in the sense that it is similar to a network equation-based example. So we have an impressed current density that is in horizontal direction. So the resulting B field in the nonlinear iron cores here will be pointing out or into the surface here. So we have a sort of two-dimensional example, and this is actually used to study the influence of the commutation versus the unhysteretic curve, which are two different methods to describe the nonlinear material behavior. And we'll just compare this to a nonlinear transient simulation, which you of course can always do as a reference solution. You just have to make sure that you compute sufficient periods in order to get into the steady state, which you can then compare with the steady state solution you directly compute from the harmonic balance method. So let's look into the description of the material law. The classical material curve to use is the so-called commutation curve. So when you do a measurement with an alternating current and you increase the field strength, you actually obtain a set of hysteresis loops, which you usually then approximate with the commutation curve, which connects all the turning points of these loops. However, if you do this, you see that for small fields, you actually have an increase here at zero B field of the permittivity. However, the reluctivity is defined as the change of the B field with respect to the change of the H field. So if you look at the periodic solution, this start of this so-called Rayleigh region, you could call it, at the start is actually not arising if you periodically transverse from plus BS, so from the saturation to the negative saturation of the field. So what you actually need as the description is the so-called unhysteretic curve, which doesn't have this almost zero slope at very small field values. Let's quickly have a look on the impact of this difference. So here we compare the results assuming the commutation or the unhysteretic curve as the material law, and we'll compare transient reference, linear harmonic, and multi-harmonic simulation. So on the left-hand side, we have a graph that shows the time history of the periodic solution. So we transfer the harmonic components again into the time domain to display the solution. And here we have one period. The transient reference solution is here now the blue line in the background. And if we see, we use 5 harmonics for the multi-harmonic simulation. We have quite some oscillation around the reference solution. If we increase the number of harmonics to 21, which is a really high value and only suitable for such a small example, we see that we converge to this transient reference solution. However, we still have substantial oscillations. If we take the linear harmonic simulation, of course, we're quite off since we can't properly approximate the nonlinear material law. If we now switch over to the unhysteretic solution, we see that actually with 3 harmonics already we can approximate the arising physical signal really well. So we have seen that this unphysical material law for periodic solutions also creates severe problems for the multi-harmonic finite element method. And this is actually caused by the shape of this signal. You see, you have rather high amplitudes, but almost zero slope or close to zero slope where the solution is small. And this is a signal that is difficult to approximate with the Fourier series. So what the Fourier series can't really well do is a signal that stays zero for a long time and then jumps to a high value. The other way around, so having this saturation for high values is much more easily approximated via a Fourier series. Okay, this was all for the nonlinear finite harmonic balance finite element method. Here you have a few references when you can find details. And of course, we have some questions for learning reinforcements.